Good morning, myself Dr. Avisankar Roy. Today we are going to discuss the interrupt part of 8085 microprocessor. So now we start the interrupt part. This is the architecture of 8085 microprocessor, and it has a total 40 number of pins, and among the total 40 number of pins from pin number 6 to pin number 11, that consists the interrupt part of the 8085 microprocessor. So we directly go to this part of the interrupt part. So here from pin number 6 to pin number 11, that consists of the interrupt part of 8085 microprocessor. Pin number 6 is trap 4.5, pin number 7 is RST 7.5, pin number 8 RST 6.5, pin number 9 RST 5.5, and pin number 10 INTR, that is interrupt request, pin number 11 INTR bar, that is interrupt acknowledgement. So there are total 4 number of interrupt, one interrupt request and another is interrupt acknowledgement. Actually interrupt is an external response or request from the external hardware to the microprocessor for external communication part. And this interrupt part can be categorized in two parts. One is hardware part and another is the software part. Hardware interrupt and software interrupt. So what is hardware interrupt? Hardware interrupt are basically the interrupt for which some pins are available. So from pin number 6, that is trap 4.5, RST 7.5, RST 6.5, RST 5.5, and INTR interrupt request, that all belongs to the hardware part in 8085 microprocessor IC. So they are called the hardware interrupt. So these are called the hardware interrupt. Here RST stands for the restart. RST is the abbreviation of the restart, and INTR is the interrupt request. Software interrupt, another some interrupt are available which we can use in within the program of 8085 microprocessor, and those instruction can be used as an interrupt also. These are called the software interrupt. So there are basically 8 number of software interrupt, and that are defined as RST 0, RST1, RST2, RST3 up to RST7. So these are the restart 0, restart 1, R2, restart 7. So there are total 8 number of software interrupt. This can be used as the instructions, and we can use this interrupt within the program. And whenever the program is going to be executed and this interrupt will be executed, so the particular job which is assigned for the interrupt will be executed. So these are the example of the software interrupt. And there are other two instructions also that are associated with the interrupt part, that is EI and DI, called the enable interrupt and disable interrupt. And if we wish that for a particular process we are going to activate the interrupt, and if any interrupt comes to the microprocessor, then microprocessor can avail this interrupt or can attend this interrupt. Then the beginning of the program we can write down enable interrupt, EI. But if we want that we are not going to enable the interrupt, we can stop the interrupt process for a particular program, execution of a program. Then at the beginning of the program we can write down the disable interrupt or DI. So if you write the disable interrupt, then no interrupt can be attended by the microprocessor. Otherwise we can use the enable interrupt or EI instruction at the beginning of the program. Okay. And INTA bar, it is active low signal, and it is called the interrupt acknowledgement. It is an acknowledge. It is not an interrupt. It is an acknowledgement with respect to the interrupt request that is sent by some external device. Say, for example, it is a microprocessor IC 8085, and it is another input-output device which is connected to the microprocessor, and if that device want to make the communication with the microprocessor and want to interrupt the microprocessor, then if microprocessor is currently executing a current program or current job, then this input device can send a request through pin number 11, that is INTR interrupt request, INTR interrupt request. And if microprocessor think that we can attend this interrupt request, then microprocessor can send the interrupt acknowledgement, that is INTA bar interrupt acknowledgement. So after getting the interrupt acknowledgement, automatically the interrupt, hardware interrupt which is connected directly with this input device will be activated, and the particular job will be executed. So there are 4 hardware interrupt, that is the trap 4.5, 7.5, 6.5 and 5.5, RSC 5.5. So among the 4 interrupt part, any one of the interrupt can be connected with the input device, and after getting the interrupt acknowledgement, that particular interrupt can be initiated and the particular job will be executed. Next part is the address. How the interrupt can be executed. So to understand the process of the interrupt part, first of all we can understand that for every interrupt, for hardware interrupt and for the software interrupt, some address has been allocated. So how to get the address? The logic is very simple. Here trap 4.5, so the value 4.5 is multiplied by the 8 and that is converted into the hexadecimal number, and we can get as a 16-bit hexadecimal number, that is 0024. So 0024 in hexadecimal, it is the address for the trap 4.5 interrupt. Similarly for the RST 7.5, 7.5 multiplied by 8, it becomes in hexadecimal 003C. So 003C is another address which has been allocated for RST 7.5. Similarly for the RST 6.5 we got 0034 address. For RST 5.5 we got 002C address. So for every hardware interrupt, for different interrupt, different addresses are allocated. So whenever this particular interrupt will be initiated, it means this particular address will be called, and the particular job or program which we want to be executed with respect to this particular interrupt, we can write the program starting from this address. So whenever trap 4.5 will be initiated, so this 0024 address will be called, and the respective program which has been written starting from 0024, this particular program will be executed or start to execute. Similarly for the RSC 7.5, so whenever RSC 7.5 is initiated, so the corresponding address is 003C. So the program which is written starting from 003C, so whenever 7.5 is initiated, so that particular program will be executed, and so on. So it is a very common procedure how to execute the interrupt part. Same thing happened for the software interrupt also. The software interrupt don't have any physical existence, so that can be used as a 1-byte instruction in a particular program like RST0, RST1, RST2 up to RST7. Same thing, that is 0 multiplied by 8 converted into hexadecimal number to 0000 is the allocated or dedicated address for RST0. Similarly for the RST1, dedicated address is 0008. Similarly for the RST2, 0010, and so on. For RST7 it is 0038. So for every interrupt some address has been allocated. Now the interrupt execution procedure. So here I have given an example. Say if a particular program is written and that is converted into the hexadecimal code, and the code is stored one by one starting from, for example, 8000 memory address. So 8000 memory address, this is our starting address of any program for an example, and from the 8000 we have loaded the hexadecimal code for a particular program. So here in 8000 one hexadecimal code for a particular program is loaded. In 8001 the hexadecimal code for RST5, which is a software interrupt, is loaded. In 8002 the hexadecimal code for some other instruction is loaded, and 8003 the halt. So if we are going to start the execution process from 8000, so in program counter by default 8001 will be stored, because if 8000 is executing currently, so next address, that is 8001, that will be executed after the ending of 8000 execution. So 8001 will be loaded in the program counter, because program counter always hold the next address that is to be executed. So if currently 8000 is executing, so program counter always hold the next address, that is 8001. So after the finishing the job of the 8000, microprocessor will check what is the content of program counter, that is the 8001. Then automatically controller go to the 8001 and the program counter will be incremented to 8002, because 8001 is currently executing, and next address that will be executed, that is the 8002. So in 8001 RST5 is written, and microprocessor will found that RST5 it is a software interrupt. So software interrupt means for RST5 some address has been allocated. What is the address for RST5? For RST5 the address is 0028. This address has been allocated for RST5. So automatically that 0025 at 28 address will be called, and that will follow the call instruction. The call instruction we know that CALL call, then we write the address, some address. So whenever call the address will be initiated, that means the program counter directly go to this particular address and the execution process is continuing. So here 8001 is executing and program counter hold the next address, that is the 8002, and program counter now is changed to 0028. So before changing 8002 to 0028, this 8002 will be stored into the stack as a backup. So here is a stack. So in the stack 8002 will be stored, then it will be changed to 0028. This is the address of RST5. So whenever 8001 is execution is the completed, then program counter value is 0028. Automatically microprocessor go to the 0028 address for the execution. So here we have written another program that is allocated for RST5 interrupt. So then hexadecimal code is written in 8028 and automatically it becomes 0029 because the next address is 0029. Whenever 0029 has been executed, then get the return instruction. When get the return instruction, what will happen? From the stack which was loaded as 8000 will be popped and it is loaded into the program counter. So next address will be changed to 8002. So after getting the return instruction, microprocessor will check the content of program counter. It is found as 8002. So controller return back to 8002 memory address for the execution and get the 8003 halt, program is stopped. So it is the main program, and from the main program using the software interrupt we can call another program called the service routine or the subroutine program. This service routine or subroutine program is directly related with this particular interrupt called the software interrupt part. That is the RST5 for an example. So it is the execution process of the interrupt. Same thing happened for the hardware interrupt also. In the hardware interrupt, if trap has been initiated or in RS7.5 has been initiated by hardware triggering, then by default this particular addresses, allocated addresses, dedicated addresses will be called from the main program, and the program which is written starting from the respective addresses will be executed, and after the finishing of the job, controller again come back to the main program. So it is the basic procedure of the execution of the interrupt part by the microprocessor 8085. So next, vector interrupt. In another way we can categorize the interrupt as a vector interrupt and non-vector interrupt. Vector interrupt means those interrupt who has a specific address called the vector interrupt. Same thing that we have already discussed in the previous slide, that trap, RST 7.5, RST 6.5, RST 5.5, all the 4 interrupt has the specific addresses. So those are called the vector interrupt, and all the software interrupts starting from RST 0 to RST 7 all have the specific addresses. So all the software interrupt are called the vector interrupt because those interrupt have the specific addresses. But some interrupt don't have any specific address, like interrupt request. It is an interrupt request to the processor by the input device before accessing any interrupt. So interrupt request don't have any address because it is a request signal. So INTR is a non-vector interrupt. So here INTR is a non-vector interrupt. That is an interrupt request. Now whenever we come to the hardware interrupt, because in the software interrupt, whenever writing the program line by line, so the line by line execution will be occur or happen, and in a particular line if we write a particular software interrupt, so that will be executed. So in the case of the software interrupt, there is no option of the occurring of multiple number of interrupts simultaneously or at a time. That means RST 7.7 or RST 5 or RST 2, multiple number of software interrupt cannot occur simultaneously in the software interrupt, but it can happen in the hardware interrupt. Say for an example, for every hardware interrupt, different devices are connected. Say for trap 4.5, device 1 is connected. For RSC 7.5, device 2 is connected. For RSC 6.5, device 3 is connected, and so on. So multiple devices are connected for the different interrupt part, and it may happen that all the devices send the interrupt request and for all the interrupts simultaneously. That means track 4.5, 7.5, 6.5 can occur simultaneously, but it is not possible to execute all the interrupts simultaneously. So then what to do? Then microprocessor will execute the hardware interrupt one by one depending upon the priority level or as per the priority level. So here is the priority level of the hardware interrupt. So it is a priority level. So arrow is going upward directions. It is the priority level. That means RST 5.5 has the lowest priority. Then RST 6.5 has the highest priority than the 5.5. Then RST 7.5 has the highest priority than the 6.5, and track 4.5 has the top priority. It means if all the 4 interrupt will occur simultaneously, requests simultaneously, then only track 4.5 will be executed first. Then after finishing the job of the track 4.5, RSC 7.5 will be executed. After that RSC 6.5 will be executed, and at the end RST 5.5 will be executed. So for the hardware interrupt, if all the interrupt occur simultaneously, then one by one as per the priority level the interrupt will be executed. Now if we want that being the lowest priority level of the interrupt RSC 5.5, we want that 5.5 will be executed first. So for example, then what to do? Because if all the interrupt will occur simultaneously, then 5.5 is the lowest priority, so it will not be executed first time. But we want that RST 5.5 will be executed first time. So what to do? Then other interrupt should be deactivated, called the masked. So here is the concept of masking and non-masking or unmasking. Masking means to deactivate something. So if I say that we mask track 4.5 or we mask RST 7.5, it means we deactivate the RST 4.5 or 7.5 for a certain time. So if we mask RST 7.5, 6.5 and 4.5 and we unmask the RST 5.5, then if all the 4 interrupt will occur simultaneously, then microprocessor will check that all the previous 3 interrupt are masked, means deactivated, but only the RST 5.5 is unmasked. So 5.5 will be executed first. Then after the finishing job of the 5.5, we can unmask our desired interrupt. Then that will be executed. So it is called the masking and unmasking procedure. So depending upon this masking and unmasking procedure, again the interrupt can be categorized in 2 parts: maskable interrupt, non-maskable interrupt. Maskable interrupt are RST 5.5, 6.5, 5.5. These are maskable interrupt because this interrupt can be masked. But non-maskable interrupt is track 4.5 is the highest priority interrupt and non-maskable interrupt. That means if track 4.5 will occur, then every time that will be executed first time. We cannot mask the track 4.5. It is the highest priority interrupt. But other than the track 4.5, RST 7.5, 6.5, 5.5 all can be masked as per our desire. So it is the 2 part of the interrupt: maskable interrupt and non-maskable interrupt. Now the question is how we can do the masking and unmasking procedure. For a masking and unmasking procedure, 2 instructions are available, that is SIM, SIM and RIM. SIM for set interrupt mask and RIM for read interrupt mask. Set interrupt mask SIM instruction is used to do the masking or unmasking any interrupt, and RIM read interrupt mask is used to read the status of the interrupt, that which are already masked, which interrupt are pending, which are unmasked. So to read the status of the interrupt for a particular time, for a certain time, we can use the RIM instructions. So these are 2 basic difference between SIM and RIM instructions. So first we discuss the SIM instruction, SIM, that is set interrupt mask. These 2 instructions are applicable on the content of the accumulator. That means for this particular instruction there is a particular control word format. It is called the control word format. Means in the accumulator we can store the 8 bit of data. So in each bit has the different significance. So it is called the control word for the sim instruction, and as per our requirement we can make the bit either 1 or 0, 1 for true, 0 for the false. That means if we want to do this particular job, make it 1. If we don't want this particular job or function, make it 0. So it is the control word for this 8-bit control word for the sim instructions. So starting from the LSB, that is B0, it is called the M5.5. M5.5 stands for mask RST 5.5. It means if we want to do the masking, so make it 1, and if we want unmasking, make it 0. Simple. Similarly for B1, bit 1, it is M6.5, means masking RST 6.5. That means if we want to do the mask, we want to deactivate the RST 6.5, the bit is 1. If we want to unmask, means activate the RST 6.5, so make it 0. Similarly for the M7.5, that is the masking RST 7.5. MAC mask set enable, means this masking unmasking procedure will be enabled if this bit is 1. Only then the masking unmasking procedure will be enabled. If this bit is 0, then the masking unmasking procedure will be disabled. It will not happen. R7.5, among the RST 7.5, 6.5, 5.5, RST 7.5 has the highest priority. So if we want to reset the RST 7.5 in the activated option, then we can make it 1. So it is the reset RST 7.5. So if RST 7.5 is unmasked, if we make the bit 1, automatically it goes to the activated state. So it will be reset. It will reset RST 7.5. These bits don't care. So whether make it 0 or 1 doesn't matter at all. So better to make it 0. SD serial data enable and SOD serial out data. In Microprocessor 805, there is a pin called serial out data and serial in data. In serial out data, one bit will be outgoing from the microprocessor to the other peripheral devices, and in serial in data pin, from the other devices the bit will come into the microprocessor to check whether the status is changed or not. So here serial communication, SOD and SID, for the purpose of serial data communication purpose. One by one the bit will be transferred from this particular pin. So this serial bus communication will be activated if this bit is 1, because it is called the serial data enable. So this serial data enable, serial communication will be activated if this serial data enable pin is 1. And if this bit is 1, then after making the changing, means masking or unmasking, this 1 bit will go to the other devices which is connected to the microprocessor through the interrupt pin. Okay, so now using the sim instruction as per our desire. So for example, we are going to unmask RST 5.5 and we want to mask other interrupt. So we want to unmask RST 5.5, so make it 0. We want to mask 6.5, make it 1. 7.5, make it 1. And mask set enable, we want to do the mask set enable, so make it also 1. We don't want to reset RST 7.5, so make it 0. It is don't care, so make it 0. Serial data enable, we want to do this enable, and SOD we want 1. So 1100, making this is C, and 1110, so it is E. So value is CE. So CE is our control word. So what we can write down here? First we write down enable interrupt. Then we can write down in the MVI, in the accumulator, load the value CE, then write down SIM. That's all. So what will happen? The interrupt will be enabled by the EI instruction, and MVI means we can load the C in the accumulator, means this bit pattern, write down the SIM instruction. So this RST 5.5 will be unmasked and other interrupt will be masked, and that will happen. Similar thing happen for the RIM instruction also. RIM just opposite. If you want to check the status, which interrupt is masked, which interrupt is unmasked, which is pending, we want to check the status, then we can use the RIM instructions. So again with the RIM instruction, so after checking the status, some data will be stored in the accumulator. We take the data, we decode in the binary pattern, and we check with this control word. Simple. So the B0 is mask 5.5. After checking, if this bit is 1, that means RST 5.5 is masked. But if it is 0, it is unmasked. Similarly for the M6.5, M7.5, IE is a interrupt enable. If interrupt process is enabled right now, so this bit will be 1. If this bit is 0, then we can understand that interrupt process is not enabled, it is disabled. I 5.5, I for pending interrupt RST 5.5. If currently one interrupt is going on, after finishing the job of the interrupt, another interrupt will be executed, so that is the pending interrupt. So if there is a pending interrupt, so that bit will be 1. If there is no pending interrupt, that bit will be 0. So same thing happened for the I6.5, pending interrupt RST 6.5, pending interrupt RST 7.5. SID is a serial interrupt, which data will be entered to the serial input data of the microprocessor. That bit will be shown over here, either 0 or 1. So using the ream instruction, we can read the status of the interrupt using the ream instructions. So that's all about the interrupt part. Interrupt part is very important part, and how the interrupt can be executed using the subroutine, using the stack, and there are some category of the interrupt like hardware interrupt, software interrupt, vector interrupt, non-vector interrupt, and maskable interrupt, non-maskable interrupt, how to mask and unmask the interrupt, highest priority interrupt, that everything that we have discussed in this part. Okay, so thank you.